Imagine a single misplaced parenthesis in a massive corporate spreadsheet,
Yeah.
right? And suddenly $10 million just completely vanishes from a company's balance sheet.
Oh, yeah. Or consider a nurse reading a patient's chart and they're calculating a medication dose strictly left to right, just like reading a book.
And they accidentally give a patient like 3 times the lethal limit of a drug. I mean, we are taught to think of math as this objective, unshakable truth. You break your arm, the medical x-ray shows a jagged white line, and the doctor points to it. Math is supposed to be that x-ray, right? A universal law.
Exactly. That's the assumption.
But what if the very way we've been trained to read it contains a hidden trap? Like a structural flaw that regularly breaks the internet, ruins standardized test scores, and, well, causes catastrophic real-world errors.
It is the absolute definition of diagnostic muddy waters. And the wildest part is that this trap is hiding in plain sight in middle school math classrooms all over the world. We rely on a system of reading symbols that is far more fragile than anyone realizes.
Welcome to this deep dive. Today, we are focusing on you, the listener, especially if you are gearing up for the TEAS or HESI nursing entrance exams. We are pulling from comprehensive prep materials to unpack the order of operations.
Yeah, specifically, we're putting the famous acronym PEMDAS under the microscope today.
Right. Our mission today is to discover how to properly evaluate mathematical expressions, explore the surprisingly human and honestly messy history behind these rules, and understand why getting this wrong isn't just about losing points on a test. I mean, it has incredibly high stakes in the real world. Okay, let's unpack this.
Let's tear down the mythology. To really master the math section of something like the TEAS or HESI, you have to unlearn what you probably think you know about PEMDAS.
Unlearn it.
Yeah. The order of operations at its core is simply a standardized sequence. It's basically a grammatical rule book used to evaluate a mathematical expression that contains more than one operation.
Like a universal translation guide.
Exactly. The entire purpose of this rule book is so that anyone, anywhere in the world, who reads the same string of symbols arrives at the exact same single answer.
And depending on where you grew up, you might know that rule book by a different name. In the U.S., it's PEMDAS. Parentheses, exponents, multiplication and division, addition and subtraction.
Right. But if you are listening in the UK or a Commonwealth country, you probably learned BODMAS, brackets, orders, division and multiplication, addition and subtraction.
Or BEDMAS in Canada, right?
Yep, BEDMAS too. All three of those acronyms are attempting to encode the exact same mathematical hierarchy. Only the letters and the regional vocabulary change. But the massive reveal here, the thing that trips up countless people on high-stakes exams, is that the precise, non-negotiable rule actually has 4 tiers.
Wait, 4?
4 tiers. It absolutely does not have 6 independent steps.
Hold on, 4 tiers. Because PEMDAS has 6 letters. Are you telling me 2 of those letters are essentially frauds? Because, I mean, please excuse my dear Aunt Sally, literally puts M before D. It explicitly tells you to do multiplication before division. Did Aunt Sally lie to generations of students?
What's fascinating here is that essentially, yes, she did.
No way.
Yeah, the textbooks she was printed in were incredibly sloppy. Early 20th century math textbooks often implied, either through clumsy wording or just the literal linear nature of writing an acronym out, that multiplication had to happen before division and addition before subtraction.
So people just assumed it was a checklist.
Right. They treated it like 6 sequential independent steps. But modern math education standards, including the exact frameworks that TEAS and HESI item writers use, are explicitly clear that this is false. Multiplication and division are co-equal. Addition and subtraction are co-equal.
Wow. So the 6-letter acronym itself is the trap. If they are co-equal, how do these 4 actual tiers work in practice?
Okay, so tier 1 is grouping symbols. This includes parentheses, brackets, braces, fraction bars, and radicals. You always evaluate the innermost grouping first.
Got it. Innermost first.
Tier 2 is exponents and roots. Then we get to tier 3, the crucial one, multiplication and division. Because they are co-equal, they are evaluated together, strictly left to right.
Okay, so it's a tie, and reading direction breaks the tie.
Exactly. Finally, tier 4 is addition and subtraction, also evaluated together, strictly left to right.
I see what you mean about the physical acronym causing the problem.
Right.
I mean, we read letters left to right, so we just assume the math follows the same sequential path. Let's look at some concrete examples to see how test makers actively weaponize this flaw. If we start with a basic case, imagine the expression 3 plus 4 times 5.
Right. So if you approach that naively, just reading left to right the way you would read a sentence in a novel, you'd say 3 plus 4 is 7. Then multiply that 7 by 5, you get 35.
Which is completely wrong. Because multiplication outranks addition. You have to jump into the middle of the sentence, do the 4 times 5 first to get 20, and then add the 3. The correct answer is 23.
Exactly.
That one is fairly intuitive once you remember the hierarchy. But let's look at the tied pair trap. This one is notorious. Imagine the expression 20 divided by 4 times 2.
Oh, yeah. This is where Aunt Sally really gets you into trouble. Test makers love this specific structure.
I mean, I would look at 20 divided by 4 times 2. Remember my flawed M before D rule and think, well, I must do multiplication first. So I do the 4 times 2, which gives me 8. Then I do 20 divided by 8, and I end up with 2.5.
But division and multiplication are on the same tier. They are tied. The actual rule is you evaluate them left to right. So 20 divided by 4 is 5. Then 5 times 2 is 10.
So the correct answer is 10, not 2.5.
Right. The source materials note that this exact structure shows up constantly on nursing entrance exams to weed out the students who just memorized the acronym from the students who actually understand the math.
You know, I like to think of these tiers like VIP lines at an exclusive nightclub. The grouping symbols, the parentheses, they own the club. They're already inside having a drink. Exponents are the top-tier VIPs. They get waved right through the velvet rope. But multiplication and division, they're in the same mid-level VIP tier.
That's a great way to picture it. And the bouncer at this club is incredibly strict. Multiplication doesn't get to cut in front of division just because it's dressed a little better or happens to be the M in PEMDAS.
Right.
If division was first in line, meaning it was written furthest to the left in the equation, division gets inside first.
And the same goes for addition and subtraction. They're just the general admission line. They shuffle in left to right based on who showed up first on the page. Now, there are a couple of other huge misconceptions we need to highlight from the sources. You mentioned earlier that radicals and fraction bars are in the top-tier grouping category. How does a line across a fraction act like a parenthesis?
Think about a complex fraction where you have a whole equation on top and another equation on the bottom. The horizontal line separating them is called a vinculum. It physically acts as a bracket.
Oh, interesting.
Yeah, you have to completely simplify the entire numerator on top and completely simplify the entire denominator on the bottom before you even think about doing the final division that the fraction bar represents.
That actually brings us to the massive exponent trap. This one blew my mind when going through the prep materials. If you see -3 squared, so that is a minus sign, the number 3, and a little 2 superscript, what does it equal? I mean, most people would automatically say 9, right? A negative times a negative is a positive.
The answer is actually -9.
Wait, if I owe you $3 and I square my debt, I don't owe you -9. Let me think this through. The exponent is greedy. It's only grabbing the 3 and it's completely ignoring the minus sign sitting next to it.
Yes, it goes back to your VIP nightclub hierarchy. Exponents outrank subtraction. The negative sign sitting in front is essentially an implicit subtraction from 0, or, a multiplication by -1.
Oh, I see.
The exponent happens first, so you square the 3 to get 9 and then apply the negative sign. If you wanted to square the negative number itself, it must be explicitly enclosed in parentheses. Open parentheses, -3, close parenthesis, square, that equals +9.
Oh, okay.
The sources say this single misconception accounts for a massive share of missed points on these entrance exams.
Well, if this rule is so bulletproof today, who actually decided that multiplication is more important than addition? Did a bunch of mathematicians just, vote on it in a room somewhere?
No, not at all. There is no Newton of PEMDAS. There wasn't a single genius who sat down, stroked their chin, and declared the laws of operations. The rule is a byproduct of how mathematical notation evolved over centuries.
Really?
Yeah. For most of history, math wasn't written with plus signs and division symbols. It was written rhetorically, in words.
Like reading a paragraph of text instead of equations.
Yes. If you look at the Greek mathematician Diophantus in the 3rd century, or the Persian scholar Al-Khwarizmi in the 9th century, whose name, by the way, gives us the word algorithm, they wrote algebraic procedures out in prose.
Oh, wow.
They would write things like, take the square of the thing and add the sum of these other two things. When you spell out math in sentences, the grammar of the spoken language does the grouping for you. Words like and then, or the sum of, dictate the temporal sequence. There was no ambiguity.
Because you don't need PEMDAS when you have commas and conjunctions telling you what to do. So when did we lose the grammar?
The shift happened during the 16th and 17th centuries. European mathematicians started building modern algebraic notation to make things more compact. In the 1590s, Francois Viet started systematically using letters for known and unknown quantities.
Okay.
In 1557, Robert Ricord invented the equals sign, and in 1637, René Descartes introduced the superscript exponent notation we still use today.
So they compressed entire paragraphs of math into a single line of dense symbols. But, I mean, when you replace the phrase "the sum of" with a simple plus sign, you lose the temporal language that told you what to do first.
Exactly. Once you have a compact string of symbols like 3 plus 4x, you desperately need a shared convention for what it means. Mathematicians converged on this organically through use. They realized multiplication and division needed priority over addition and subtraction because it mirrors the underlying algebraic structure of a term.
Wait, so when you say algebraic structure, do you just mean that multiplication is basically a zipped-up version of addition? Like 4x is just x plus x plus x plus x, so you have to unzip that first before you can add the 3.
If we connect this to the bigger picture, the order of operations is really just formalizing what algebra already means structurally. In that expression, 3 plus 4x, the 4x is a single term. The plus sign is just combining that entire term with the number 3.
Okay, that makes a lot of sense.
Right. Multiplication inherently binds things into terms tighter than addition does. The rules just reflect the reality of the math.
Here's where it gets really interesting.
Yeah.
Because the underlying structure was always there, mathematically. But PEMDAS, the acronym we all stress over, that's just a 20th century American teaching device. It was layered onto this centuries-old convention just to stop kids in classrooms from getting different answers.
Yeah.
The attempt to make it easy for students, ironically, created a brand new misconception that teachers now have to spend all their time fixing.
And even with all that centuries-old structural reality, human notation still has gray areas. We haven't perfected the language. There is a lifestyle difference in mathematics today regarding situations where you just squish a number right next to a parenthesis, like a 2 next to an open parenthesis with an x inside.
Right, where there's no explicit multiplication sign there.
Exactly. And mathematicians call this implicit multiplication by juxtaposition.
Okay, so most modern textbooks, and essentially all standardized test writers, treat that juxtaposition as ordinary multiplication. It gets no special VIP treatment. It just follows the standard left-to-right rule with division. But some mathematicians, particularly in older physics and algebra texts, treat juxtaposition as binding tighter than explicit multiplication or division. They see that squished together 2 and the parenthesis as a single welded unit.
Which brings us to the viral equation from 2011. 6 divided by 2, open parenthesis, 1 plus 2, close parenthesis.
Oh, I remember this.
Yeah, 6 divided by 2 times 1 plus 2. This thing broke Facebook and Reddit. Millions of comments. Real disagreement even among people with solid math backgrounds.
Let's work through both camps. If you follow the modern standard, the strict left-to-right rule, you do the parentheses first. 1 plus 2 is 3. Now your equation is 6 divided by 2 times 3.
Right.
Left to right, 6 divided by 2 is 3, and 3 times 3 is 9. So you get 9.
But the other camp says the 2 is squished right up against the parenthesis. They use the older type binding convention. They do the parentheses first, 1 plus 2 is 3, but then they treat the 2 multiplied by 3 as a single glued together term.
Ah, I see.
So they do that multiplication first, getting 6. So the equation becomes 6 divided by 6, which is 1, and both camps can cite real published textbooks to back up their method.
Wait, so you're saying math, the most rigid subject on Earth, actually has subjective style differences?
It's a convention, a language. Like any language, there are dialects. And this leads to incredible real-world failures. There are documented cases of graphing calculators from the exact same manufacturer, Texas Instruments, disagreeing with each other.
That's crazy.
Older TI models and newer models evaluate expressions with implicit multiplication differently because their firmware was coded with different precedence assumptions. You could literally have 2 students with 2 different calculators taking the same test, and the machines give them entirely different answers based on how the programmers interpreted juxtaposition.
That is terrifying for a student.
Yeah.
I mean, sitting in a silent room, trusting a machine that has a different dialect of math than the one they were taught.
This raises an important question. How do high-stakes exams handle this?
Yeah, how do they?
The answer is they don't. Well-written exams, explicitly including the TEAS and HESI, avoid this ambiguity entirely. They will not write an expression that ambiguous. They stick strictly to using explicit multiplication signs to ensure there is only one undeniable interpretation.
Okay, so they won't trick you with ambiguous formatting, but they will absolutely test your knowledge of the strict rules. We've talked about history, we've talked about calculators, we've talked about viral memes. So what does this all mean? Why does a future nurse or, a business analyst need to care about this beyond just passing a test?
Let's look at tech and business first. Order of operations is the traffic control layer of every spreadsheet and programming language on Earth. Every formula in Excel obeys these rules blindly. The sources highlight research by Raymond Pankow, who spent decades studying spreadsheet reliability in corporate environments.
And what did you find?
He found that routine corporate spreadsheets are completely riddled with uncaught formula errors. A massive number of these errors trace back to exactly this, missing parentheses or sequencing mistakes.
Right, because in a complex financial model, a spreadsheet might pull data from a dozen different tabs, multiplying quarterly revenue by a tax rate, then subtracting expenses. If the analyst forgets one set of parentheses, the computer does the multiplication first instead of the subtraction. The computer doesn't know what you meant to do. It only knows what you told it to do, strictly following the hierarchy.
Exactly. Millions of dollars can vanish from a forecast because of one invisible grouping error. But for the nursing students listening, the stakes are literal life and death. You will be doing dosage and IV drip rate calculations on the floor. These are built on multi-step formulas. You might have to take the desired dose, divide it by the dose on hand, multiply by the quantity, and divide by the time the drip needs to run.
And if you get the sequencing wrong because you did addition before multiplication, or you messed up the left to right tiebreaker,
the patient gets the wrong dose. Patient safety research explicitly flags arithmetic sequencing errors as a major contributor to clinical medication errors. When TEAS and HESI test you on the order of operations, they aren't just making sure you pass 7th grade math.
it's a screening check.
It is a vital screening check. They need to know that a future nurse can reliably execute a multi-step numeric procedure in the exact order it demands without relying on a flawed mnemonic. They are testing your structural reliability.
It's not just abstract rules. It's a framework for saving lives. As we wrap up, let's synthesize the biggest booby traps you're going to face on these exams. We know PEMDAS is 4 tiers, not 6 steps. The biggest thing to remember is those ties.
Yes, multiplication does not automatically outrank division. Whoever is first in line on the left side of the equation gets in first. You also have to remember that every grouping symbol acts like a parenthesis, even the ones that don't look like them.
Right, the vinculum. That horizontal line on a fraction bar or the line over a square root screams, simplify what's inside me first before you move on. And you can't forget the negative exponent trap.
Yeah.
-3 squared without parentheses is -9, because that exponent is greedy. It only cares about the number it's touching, not the minus sign.
And when you have symbols nesting inside each other, just remember to work from the innermost grouping outward. Find the deepest parentheses first, evaluate them, then step out one layer at a time. It requires patience, not just memorization.
If you master that patience, you'll be bulletproof on exam day. Before we go, I want to leave you with a thought that really expands on everything we've explored today. The order of operations is essentially just the grammar of mathematics, a system we humans developed over centuries to resolve ambiguity when we compressed words into written symbols. We've seen how calculators and Excel spreadsheets strictly enforce this human grammar, sometimes resulting in disastrous errors when our inputs are flawed. So, how might our mathematical rules need to evolve again? We are increasingly communicating purely through computer code and artificial intelligence, environments where implicit human assumptions simply don't exist. Will AI, which doesn't have the intuition of human context, force us to invent an entirely new grammar for math?
It's a fascinating frontier. The X-ray machine of math might be getting a massive firmware update soon, completely removing human dialects from the equation.
It might feel like a clean, objective X-ray, but as we've seen today, that X-ray is only as good as the human conventions that built the machine. You've got to know how to read the film.
Thank you so much for joining us on this deep dive.
Thank you for listening. Good luck on your exams, and keep questioning everything. We'll catch you next time.